Newton shows about philosophy of math. And then next, what philosophers could ask next about each one? Because, of course, the point of this is to go on. The point of this is to lead on to more questions. These are not all the important mathematicians for philosophy of math. I'm not claiming that I'm telling you the 14 most important philosophers of math. Archimedes isn't here, Hypatia, Newton, Descartes, lots more. It's the 14 that best fit into this lecture series, the ones that I have points I want to make about. Starting with Euclid. The rest will all be much more recent. But I do want to start with Euclid, around 300 BC. We don't know what he looked like. That's a possibility of what he might have looked like. The historic facts aren't well known. We do know that the 13 volumes of his Elements of Geometry replaced all the earlier Greek geometry books. We have fragments of geometry books before Euclid. Various people wrote down and said, oh, there was this book, there was that book. We can learn a little bit about some of the books that existed before Euclid, but they're basically gone. In Western literature, you may know Homer, who wrote the Iliad and the Odyssey, 2 long epic poems. We know there were epic poems before his, because people wrote down and said, oh, there was this one, there was that one. We know there were. But they're all gone. Homer displaced all the others. And similarly, Euclid displaced all earlier geometry books in Greece. It is axiom, theorem, proof mathematics. He has his axioms, states a theorem, gives a proof. Now, there are lots of ways to do mathematics besides axioms and theorems and proofs, and there have been many historically important patterns of mathematics other than that. But I'm interested in this pattern for this lecture series. I'm going to talk about how this pattern where you state your starting points, you state what you're going to show, and then you prove it from those starting points. That's the conception of mathematics, not because I think it's the only thing important to do in math, but it's because it's the conception that I want to stress that's produced foundations of mathematics and ontology of mathematics. The earliest known version of Euclid, the earliest version we know, is from probably 600 years after it was written. We really don't know what it looked like at first. We know that it was rewritten several times, and the earliest one we have is from about 600 years after. But that version has been a paradigm for mathematics to this day in the West. There are still colleges teaching geometry from Euclid's Elements. They're doing it for historical interest, but they are still doing it. Until 100 years ago, there were high schools that taught geometry from Euclid's Elements because that was the best book they knew. The 2,000 years after it was written, it's still being used. It gives a surprisingly efficient but surprisingly long proof of the Pythagorean theorem. The Pythagorean theorem is the one saying if you have a right triangle, then the square on the hypotenuse is equal to the areas of the squares on the other two sides. It's a famous theorem. We know that there were much shorter, simpler proofs than Euclid's before Euclid. Because a few people wrote them down in history books, but those proofs disappeared. But somehow, I'll talk more about it as we go, but somehow this much longer proof, more rigorous, replaced all the earlier ones. So that's, okay, now we're getting closer to the time that I'm going to focus on. But all of these people start from Euclid. All the first few people we're going to talk about start from Euclid. Buick Bridge, he's not a research mathematician. He was an educator and an author. But certainly he took Euclid as his model. This is a picture of the college he went to. It looked like that when he went to it. Well, the grass wasn't as nice. This grass was mowed by an electric lawnmower. But basically, his college looked like that in 1790 when he was there. He's noted for learning, teaching, and writing mathematics, not for research in mathematics. He was senior wrangler, which has been called the greatest intellectual achievement attainable in Britain. What is senior a senior wrangler? The wranglers are the top mathematics students at Cambridge University. Mathematics was the most prestigious major, and the top mathematics students were called wranglers. It's not obvious why they were called wranglers. You can't really worry about the English meaning of the word, but they were. And the senior wrangler is the one who does the best on the exam. They score the top on this examination that's given every year. Extremely competitive. You really have to drive to do it. The senior wranglers do not all become mathematicians. Li Xianglong of Singapore was senior wrangler. Yeah. But most of them become mathematicians and physicists. At 19, he was a scholarship student. He served meals and did other things for the wealthy students. He was a student. He was admitted there, but he had to do work for wealthier students. He wrote a number of successful books, very successful books, including an elementary treatise on algebra. People across Europe, England, and America studied from this book. At 45, he became a Fellow of the Royal Society. It is an extremely prestigious appointment. The main thing I'm interested in, he taught students to use Newton's formula for any power of a sum of quantities. So Q here could be any rational number. So Q, this might be the square of that sum, if Q is 2. It could be the cube of that sum. It could be the square root if Q is 1/2. The Q could be any rational number. So you probably know Newton's binomial theorem. If this is a natural number, 2, 3, 4, 5, then you know how to expand the sum. But for any rational number, you can get this infinite series. Björkbridge teaches this. This is the top result in his book. He does not define, okay, I probably have this on a slide. He gives no definition of quantities. He doesn't say what quantities are. He doesn't say they're real numbers or rational numbers. He just doesn't say. He doesn't say what powers are. We know what the square is. You take a number and multiply by itself. The cube, take it and multiply by that. Roots he's not as clear about. He does not say what the sum of an infinite series is. He manages to teach people to use this without defining any of the terms. Of course, this is the 18th century. This is the 1700s. But this was university-level mathematics at the time. Then we come to Leopold Kronecker. This is a research mathematician. Yeah, great mathematician. Numerous achievements in pure algebra, in number theory, in mechanics. Extremely important mathematician for a lot of things. He had a clear grasp of what an algorithm is, long before anybody else. Even to this day, algorithm is it's sometimes vaguely defined. Basically, I would say an algorithm is a computer program. It's definite instructions that you can follow step by step to solve a problem. You're given data, you take these steps. You don't need to think creatively about how to do it. An algorithm gives you instructions. You follow the instructions, you get the answer. I mean, we're all used to adding two-digit numbers. You know what to do. You know 3 plus 5 is 8. 2 plus. I mean, you know instructions for how to do that. And Kronecker was one of the first people to grasp the idea of just a definite routine, simple instructions that you can certainly follow that will always give you the answer in a finite number of steps. When people say in a finite number of steps, there's no other way to do anything. We only do things in a finite number of steps. But the idea that it can be done routinely, that there's definite instructions. Kronecker really understood that before other people did. He's very interested in calculations that are possible in principle, even if not feasible. And that's a distinction that I'm going to come back to a lot. We have, as you know, we got computer programs. You give them any whole number, and they will find the prime factors. You can factor a number into primes by an algorithm, by definite procedure. But you probably know that if that number is 200 digits long, it's going to take a while. And if that number is 1,000 digits long, it's not going to get done. So we have an algorithm. In principle, we know how to do it. But that any algorithm becomes infeasible when you give it large enough inputs. And that's a distinction I'm going to want to stress a lot during the lecture. Because a lot of people at his time weren't interested in this idea. They were saying, I want to know how to actually solve problems. I don't want to know how to solve them in principle if I had enough time. I want to know how to actually solve them. But Kronecker was right to stress this idea is also important. But it's different from being feasible.
The feasible in modern computer science means in P, polynomial time. You can. But did he have some kind of classification of problems which are
No.
different? Okay.
No. And of course, feasible it depends how important the problem is.
Okay.
I think for most purposes, factoring a 400-digit number into primes is infeasible. But you could do it if it's important. If it's important enough to get your government or mine to put all their computers on that project, it could be done. So feasible is a complicated thing. And, we'll talk more about that. Here's a very practical problem that he solves. Given integer polynomials, p of x, q of x, two polynomials in one variable, integer coefficients, you want to multiply them together. Well, you and I can do that if, say, they're cubic polynomials and the coefficients aren't too big. But if they're 89th degree polynomials, it's going to be a lot harder. And if you're doing millions of them in a computer process, it's going to be hard. He shows how to calculate the polynomial product immediately from numerical products for large powers of 2. You don't actually need to work with large polynomials. You can just look at their values, and you can recover what the coefficients have to be from them. This is, in fact, a way to make it feasible to multiply more and larger polynomials quickly than if you tried to do it directly by the routine that we all learned in high school. This is his discovery. What you do is you take large enough powers of 2 that their different powers are incomparable to each other, and then you just ask which powers of 2 occur in the product of those. Here's something that's important but less feasible. Factoring integer polynomials. You take some integer polynomial, I don't know, an eraser.
Yeah.
let's say 3x to the 5th plus 2x to the 4th minus x cubed plus 7. Can you factor that into integer polynomials? Now, for all I know, it's obvious to somebody. I just made this thing up. It's probably hard to do. Normally, factoring polynomials is not so easy to do. But it can always be done. There's an algorithm for factoring integer polynomials, and let me point out, you can't necessarily find the solutions to that. You may not have solutions expressible in radicals, in roots. But you can get a computer program that will factor it as far as it can be factored in integer polynomials. Likely enough, that is as far as it can be factored. Most polynomials are irreducible. Probably you can't split this at all. I don't know that. But Kronecker gives the algorithm that takes any integer polynomial, gives its factors, and that people use. People use his algorithm for this. You can find all the integer polynomial factors, even over algebraic number fields. That's something we're going to come to. What that means is, maybe I'm not just allowed to use whole numbers, 3, 7, 9. Maybe I'm also allowed to use the cube root of 5. I pick some algebraic irrational number that I'm also allowed to use. His algorithm still works even when you admit a finite list of algebraic numbers that you're also allowed to use. And his Sturm algorithm, locate all the real roots of any integer polynomial. I don't know where the roots of this polynomial are. What do I see about this? If you look at what's the graph of this look like? Well, far away it looks steep. It's like a 5th degree. It's like x to the 5th. Far away. Closer in, because that's added, that's subtracted. I'm betting it looks something like that. It's only got one real root. I don't know that, but that's the kind of thing that might happen. Kronecker gives an algorithm not only to find out how many real roots it has, but also to locate it inside an interval. How big an interval? You get to pick. You get to say, I want to know to within some interval that's 1 unit long. I want to know to within some interval that's 1/10 of a unit long. His algorithm will locate that to any stated precision. Of course, not perfectly, because we don't have a way to perfectly solve higher degree equations. But his algorithm will locate the real roots. And these are things that, these algorithms are not very fast. You can do them, and people do them. They're implemented in real software. But people who have problems that really depend on them say, okay, they're not very efficient. They're not as efficient as we would like. Here's something with a huge impact in number theory, but very limited feasibility. The Kronecker-Weber theorem in Galois theory, what does that say? I will say he stated this, it wasn't proved for a long time. Yeah, if you take the rational numbers, and let's extend them by, well, for a start, say the 17th root of 3. So just take the rational numbers plus 17th root of 3. This has a Galois group. The Galois group, well, I'm not going to explain this in a lot of detail, but the thing is, let's extend it by anything, by any algebraic irrational. We talked about all the different ways you can move this around without moving the rationals themselves. We talked about the symmetries of this field. Well, okay, the easy example is, let's just add a square root. Let's add square root of 2. You can move this around. The integers there are of the form a plus b times square root 2. We take any integer and any integer multiple of square root 2, and we can add them and multiply them and subtract them. But you could carry that over to a minus b square root of 2, because you know 2 has 2 square roots. You might say a positive square root, a negative square root. Well, you would if you're doing real analysis. And you can switch them around. There's sort of 2 ways to add square root 2. Any algebraic number field has different ways of mapping into itself. But if those ways form what's called an abelian group, then that field is contained in the rationals extended by some root of unity, a cube root of unity, a 19th root of unity, complex 19th, some number. Extensions that have a very special kind of Galois group are all contained in very special kinds of extensions. And this is why class field theory exists. Okay, here's the part to take home that I can explain to you. Class field theory is a very advanced part of number theory, and the reason it works is because Kronecker gave 2 ways to look at certain extensions and showed their equivalent. People would love to be able to compute answers to various problems in number theory this way. This makes the answers computable, but not easily computable, so that the computations here are really not very feasible. Richard Dedekind. I like Dedekind a lot. I just think I would have liked to know Dedekind. Doesn't he? He looks like a good guy there. Kronecker was not a very good, nice guy. I think he was very smart, but Dedekind was smart and also nice. He's best known for giving axioms for natural numbers and real numbers. He's best known for this basic mathematics. But he also created modern algebraic number theory. He created the current approach to all this stuff that I've not explained very clearly over here. All the ways that people look at algebraic extensions of the rationals. The framework for that is his, by using the ideals and algebraic integers. I'll explain those better in the series. He did create the framework for the modern subject. He gave many specific results in number theory. That's why people use his framework. And he also used these ideas, called ideals, for what he calls a fully general and rigorous proof of the Riemann-Roch theorem in complex analysis. So he takes his number theory and he applies it in calculus of complex numbers and makes it work. Makes it really prove deep theorems. I think that philosophers of math, we don't always understand the depth of the issues, the depth of the results that are being proved by some of the techniques we look at. I do not have time in the whole series to really explain the depth of the Riemann-Roch theorem, but I want you to know that there's substantial theorems here. It's not just that he offered a way to look at the subject. He proves important results by looking at the subject that way. And he makes connections between number theory and complex analysis, also between other things. This took decades to be absorbed. For the next 100 years, people were making deeper and deeper extensions of this result. Again, I think philosophers should realize how continuous this history is and how these ideas are really do get developed further and further. Felix Klein. He he liked the new ideas of his time. Now, his time is the middle of the 19th century, well, late 19th century, mid to late 19th century. And he jumps on these ideas. He's, he looks at topology. We'll say a little bit more about that in a minute. Non-Euclidean geometry. You probably know Euclid's parallel postulate says if you've got a line and a point that's not on the line, this is one way to state the parallel postulate, there's a unique line here that doesn't meet that. Every line has a unique parallel through any given point. And people wondered, can't I prove that from the other axioms? They said, this looks like something you should be able to prove, that there's a unique parallel. And it occurs to people through the 19th century that no, there's other geometries where there's several lines through that point that never meet this one. You can have, or there's other geometries where no two lines fail to meet. Every two lines meet. You can give geometries that don't look like Euclidean geometry, and they make sense. And at first this was just a curiosity to people. Okay, that's cool. You could do geometry with a different kind of parallels. If there are several parallels, then the angles of a triangle don't add up to two right angles. Triangles are sort of like this. If there's several parallels, the angles in a triangle are sharper than they would be in Euclidean geometry. But he shows that this geometry exists. But more than that, more than that, he makes this work. He uses topology, non-Euclidean geometry, group theory. Group theory is the subject of permutations, of ways of changing things around. And topology, I would say, have you seen the Klein bottle? It's a shape. It looks like a bottle. Does this drawing look like a bottle to you? This is like glass, and you can see through. The dotted lines are the parts where you're looking through. It looks like it has an inside, but it doesn't really have an inside. If you started inside here, and you went around through that neck, you'd be outside. It doesn't have an inside and an outside. The surface doesn't have two sides. And again, these were curiosities at the time. People said, hey, that's interesting that we can define shapes like this. You can't embed this in three-dimensional space. That's why it's drawn like this. But you could embed it in four-dimensional space. Can you picture this bottle in 3 dimensions? Now allow time. Picture the back part of it at this time, and now let the back recede into the past, follow around this neck, and now let's travel back into the past and join out here. We have this where it looks like it's going through itself. Have that happen at a different time. So there's no one time where this is going through the bottle. So if we allow time as a fourth dimension, this thing doesn't cross itself. But if you're picturing it in 3 dimensions, it really is. This neck is going into the bottle here. But in 4 dimensions, it doesn't have to. And people thought, well, that's interesting. And it is kind of interesting to realize this can happen. But what Klein does is he uses these new ideas for substantial results in complex analysis, in differential equations. He says these are not just curiosities. These things really work. These things solve classical problems in mechanics, in number theory. These new ideas aren't just interesting, they work. They work for old purposes. He's most famous as a mathematical promoter and organizer. He got a huge amount of money from the Prussian government to build a great mathematics department at Göttingen University. I don't think I had another thing. Yeah. He built this at Göttingen. He hired David Hilbert into that program. He's famous for this Erlangen program in geometry. He wrote an essay about how should we start doing geometry? How should we do geometry from now into the future? And he explains how we should use group theory in this. And And he was right. This is how geometry started being done. People really did start pursuing this idea. He's much more famous for coming up with ideas than for the actual theorems he proved. He did prove important theorems, but he's more famous for recognizing the latest ideas and making them work. And he was a champion. He hired David Hilbert. He hired Emmy Noether. He shaped mathematics. He had a huge influence on American mathematics also. He got his students hired at American universities, and they then decided what would happen in American mathematics. Henri Poincaré. Oh, here's a giant. This is a universal mathematician. He dominated the mathematics of his time in a way that nobody has since. And just nobody has been so obviously the strongest mathematician of their time as Poincaré was. For one thing, there's many more mathematicians today than there were in his time. Nobody will ever dominate the field again the way he did. That is supposing, as we all hope, that the world remains at peace and we're not bombed back into the Stone Age and someday there's only 5 mathematicians again. But if the world develops normally, no one will ever be able to dominate the subject again the way Henri Poincaré did. He was strongly grounded in differential equations, and especially celestial mechanics. I want to stress very concrete classical mathematics. Problems that you could have explained to Isaac Newton, he would have understood the problem. He could not have solved it, right? I mean, they get solved over the next 100 years, 200 years. Well, Poincaré was a major part of getting them solved. Classical problems, celestial mechanics, the motions of, say, the solar system. What can we really say about the motion of the planets around the sun? Okay, we can write down Newton's equations. We can't solve them. That's too hard. What can we say about them? Poincaré was very powerful at doing that, but he does it a little bit like, well, okay, he brought really huge skill to this and unprecedented rigor. He really did this more carefully, more accurately than anyone had done before. And he did it by inventing new ideas. He also, while he's doing this classical work, he's doing it by inventing new ideas, algebraic topology, qualitative differential equations. That is, instead of looking at what the solutions are, describe what they're like. Describe what they're like without knowing what they are. What can you tell me about what they're like without actually knowing them? Well, he's a great champion of doing that, and he makes it work, he makes it important. He was probably the first important mathematician to use Cantor's set theory. George Cantor comes up with this theory of transfinite sets. We sometimes think that Henri Poincaré was opposed to Cantor's set theory, completeness impression. He was really the first mathematician to use Cantor's set theory in differential equations, in this very classically motivated field where we really want solutions. He's using Cantor's set theory to get those solutions, and very deliberately advertising that he's using it. He wrote one paper on number theory, and that one paper on number theory, the problem became André Bayes' geometrized number theory. You might not have heard of André Bay before, French name, André. This paper became that, and that became 20th century number theory. Late 20th century number theory all comes out of Bayes' vision, and Bayes' vision comes from Poincaré's paper. One paper, and he plants this vision. His inventions are deeply intuitive. You read them and you think, wow, I need to learn this. This is great. I see what this is about. I see how much this is going to do. I've got to learn the details, and you cannot, because it's desperately unrigorous. The details are terrible. He gave a really new level of rigor to classical calculations. That part he did much more rigorously than anyone before. But his new ideas, no, it took decades for other mathematicians to get them right. And they spent those decades because you could see these were great ideas. But there was a lot of work to get them right. David Hilbert. The most universal mathematician since Poincaré. Okay. You can't match Poincaré. But Hilbert comes close to it. Hilbert is not as strongly grounded in classical questions of mechanics and differential equations. He's in the more theoretical parts of mathematics. With Felix Klein's support, okay, everything for the first half of Hilbert's career, he's constantly working with Felix Klein. He gathers a school of mathematicians around him, does powerful work, often collaborative. Very often Hilbert has co-authors, he has co-workers in, algebra, number theory, differential equations, mathematical physics, logic, not as strongly in differential equations and mathematical physics as Poincaré, but in everything, including logic. And now that's something Hilbert does more than Poincaré. Poincaré, we'll talk about his ideas on logic, but Hilbert pursues those ideas more effectively than Poincaré. Lautenbauer, leading topologist. He's famous for creating intuitionistic mathematics. If you've heard of him, you'll have heard of him for his intuitionism. But he first became a topologist, a standard topologist. He made the first major progress on Hilbert's fifth problem on Lie groups. You don't need to know what the problem is to know. You may have heard of the Hilbert problems. Hilbert gives a talk to the International Congress of Mathematicians, 1900, lays out 20 problems, I think he had 23 written down, that he thinks might guide 20th century mathematics. Most of the ones that could be solved have been solved. Some of them are kind of open-ended. There's no definite solution. But the ones that had solutions have been solved. So it's a little too late to do this. But you solve the Hilbert problem, you become famous. Well, Brouwer made progress on one of Hilbert's problems. And he brought new rigor to topology. The Poincaré's topology, as I say, he left it completely unrigorous. Powerfully insightful, productive, but not rigorous. Brouwer brings unprecedented rigor to topology. He proved great theorems on the topology of manifolds by this method that's still being used today. A manifold is a topological space where, okay, here we go, these are a pair of holes. This is like, some babies chew plastic things like this sometimes. Here's a ball. It doesn't look like a ball, it looks like a circle, but I want you to think of a ball. Now here is what we call a torus. It's a ball with a hole through the middle, an inner tube, a tire. This has two holes in the middle of it. Topology is studying shapes like this, and he makes that more rigorous than it ever was before. Okay, I'm going to come back through these people. So there's Emmy Noether. Should I say she's the greatest woman mathematician? You have to. She's the greatest woman mathematician. She's a great mathematician, She's remembered today for algebra, but she first starts by proving conservation theorems these are about conservation laws in physics that settled the debate in general relativity. She first created a method for doing mathematical physics. And then she created modern algebra, the way abstract algebra is done now, the way commutative algebra is done now. This is her idea. She sets up modern algebra, uses this to organize number theory, led other people to use this algebra to create algebraic geometry, algebraic topology, modern cohomology theories, if you've heard the term cohomology theory, or you will through the lectures. cohomology theory is still, I think, to a lot of people considered ultra-modern. It's Emmy Noether's idea. She gives the basics of that. Saunders-MacLean was her student. We will be coming to Saunders-MacLean. So there's this continuity of Klein to Hilbert to Noether to MacLean. André Weil. Now here's one I think a lot of philosophers have not heard of. You should hear of André Weil. He's not in the army there. He didn't go in the army. He's just hiking. This is his hiking clothes. French mathematician. You've probably heard that number theory is the queen of mathematics. Gauss said this. The finest part of mathematics, the queen of mathematics. Fermat, Euler, Riemann, Hilbert, all hold this view that number theory is the peak of mathematics. But the truth is that very few early 20th century mathematicians knew any of it. Because it's not applied. You don't use it in engineering. You don't use it in physics. You don't use it in geometry. Well, you didn't used to use it in geometry. This finest part of mathematics was really almost unknown to most mathematicians in, say, 1920. There's a handful of people. They makes it geometry. I think a lot of philosophers have not understood how thoroughly number theory has become a part of geometry now. It's very organized in geometric terms. Weil starts that, sets it in motion, puts it at the top of the agenda for pure math by 1950. By 1950, this is clearly, it's not just the finest part of math, it's the most active part of pure mathematics, it's the most prestigious research projects. And André Weil is the one who did that. André Weil was not a very friendly person, but he was influential. He did that. Posed what are called the Weil conjectures. Well, what are the Weil conjectures? Okay, they don't look like number theory. They're very technical looking. But just posing these conjectures in number theory, just offering the thought that they might be true, was immediately recognized as a great achievement. It was, as people looked at them and they said, I don't know how you could think of that. It's so beautiful, it must be true. It was a statement that you thought, nobody could think of that unless it was true. But very hard to prove. They proved impressive special cases of it. It took 2 or 3 Fields medals to prove it, to finally prove it. It depends which parts of Serre's work you think got the Fields medal. But this became the leading project in number theory in the second half of the 20th century, and the most prestigious project in pure math, I would say. He also is part of the Taniyama-Shimura Weil conjectures, which nobody can decide what to call them, because it's not clear who did, but he was part of that. Also, this conjecture was immediately seen as a deep problem. I'll come to that in the lectures. I will say conjecture is not a perfect term here, because none of the 3 quite thought this thing was true. What I call the Weil conjectures, he thought they were true. This was really a question. You didn't know if it was true or not, but just raising the question. So besides that he was extremely powerful in proofs, the questions he raised were considered extremely important. The questions themselves were achievements. And